Hello everyone, in this TRCR tutorial number 71 we will explain how to make a nonlinear LDMOS Cgd capacitor by using a diode model. As we saw in the TRCR tutorial number 70, the drain gate capacitor in a LDMOS is nonlinear and denoted CDEP because it is a depletion capacitor. This nonlinear capacitor behaves like a PN junction capacitor inversely proportional to the square root of the voltage VDG when VDG is positive. Thus, to create a specific LDMOS model using the basic SPICE simulator, we can replace the CDEP with a PN junction diode. Of course, since this is a diode with the N side connected to the drain and the P side to the gate, when the drain is greater than the gate, the diode is in reverse, enabling switch SW1 to be activated. Conversely, when the drain is less than the gate, the switch can be opened to prevent the diode to be biased in direct and clamp the gate at 0.6 volt over the drain. When SW1 is open, SW2 is closed to connect the capacitor C, which is equivalent to the maximum value of the depletion capacitor. If we study a turn-on switching by plotting the drain voltage VD and the gate voltage VG as a function of time, we see that on the left, the drain is higher than the gate voltage, so VDG is positive. Diode D can then be connected with SW1 closed because it is in reverse and provide its depletion capacitor model. This capacitor model, inversely proportional to the square root of VDG, ensures the strong nonlinearity of the drain switching with a faster DVDT slope when the drain voltage is maximum and the lowest slope when VDG equals 0. On the right, when the drain voltage is lower than the gate voltage, capacitor C is connected with a switch SW2. This capacitor C is a classic linear capacitor model, replacing the maximum depletion value when VGD equals 0. The drain dV over dt is therefore constant and equal to the maximum. At the top, we see the closed switch. At the bottom, we see the open switch. By definition, an ideal closed switch has zero impedance. The model can therefore be replaced by a resistance R equal to 0. By definition, an ideal open switch has infinite resistance. The switch can therefore be replaced by a high impedance. My simulation experience has often shown me that switching the SPICE model resistance from 0 to an infinite value can result in the SPICE model not converging or in a longer convergence time. Furthermore, if the switch is used to connect a capacitor when it is open, thus the resistance R being infinite, the connection node between the capacitor and the infinite resistor is a high impedance floating node, which again do not help to the convergence of the SPICE simulator. A trick to get around this problem is to replace the switch by a voltage source. Of course, for the ideal closed switch, it is obvious that we must replace the switch by a voltage source equal to 0. To replace an open switch with a voltage source, we must define the voltage equal to the voltage across the switch when it is open. The element connected to the open switch must have a voltage of 0 volt since no current flows due to the open switch. In our case, if the switch and the element in series are connected between the drain and the gate, if 0 volt is applied to the element, the voltage across the switch will be the voltage between the drain and the gate VDG. The open switch can then be replaced by a source voltage equal to the voltage VDG. Thus, the complete circuit with the capacitor connected, the gate and drain of the NMOS is shown above with a 0 volt voltage source replacing the closed switch. In the case of an open switch, the open switch is replaced by a voltage source equal to VDG. The switch must be closed when VDG is positive and open when VDG is negative. Simulator convergence is less problematic by forcing voltages rather than controlling the high impedance node. Furthermore, by using the voltage source to replace the switch, the voltage across the disconnected capacitor is 0 volt and thus not a high impedance node. To detect the sign of the drain gate voltage, the first step is to convert the voltage to current using the spice-controlled source G, which transforms voltage into a current with a gain of 10 micro. A timing diagram illustrates an example where a constant voltage VB crosses a decreasing voltage VA. This means that a delta V equal to VA minus VB of 1 volt will be replaced by a 10 microamp current source indicated in red on the timing diagram. After transforming the voltage into a current source, using two diodes, D-pos and D-neg, we can separate the current IG into two separate branches to obtain the positive and negative current. When delta V is positive, the current IG flows through D-pos and generates the voltage V-pos. This is shown in the V-pos versus time diagram. When delta V is not positive, V-pos equals 0. When delta V is negative, the current IG flows through D-neg and generates the voltage V-neg. This is shown in the V-neg versus time diagram. When delta V is not negative, V-neg equals 0. With 10 micro and 100 kilo ohm, the delta V over V-pos or delta V over V-neg gain is equal to 1. To obtain the final nonlinear capacitor model Cgd using the voltage source to replace the resistive switch, we need to use a second spice-controlled source E that transforms one voltage into another voltage with a gain of 1. The generator E can be seen as a follower taking a voltage with an infinite input resistance and generating a pure ideal voltage source with 0 impedance. This generator E will be used to measure the delta voltage VDG between the drain and the gate and to convert this voltage into a current IG with a controlled source G. Using the diode D-pos and the 100k ohm resistor, we will generate the signal V-pos, which represents only the positive portion of the voltage VDG. The voltage V-pos is equal to 0, which is equivalent to the switch being closed, when the voltage VDG is negative, as shown in the small graph of V-pos versus time. The current minus IG flowing through the diode D-neg and the 100 kilo ohm resistor generate the signal V-neg, which represent only the negative portion of the voltage VDG. The voltage V-neg is equal to 0, which is equivalent to the switch being closed, when the voltage VDG is positive, as shown in the small graph of V-neg versus time. Since the switch is closed when the voltage VDG is greater than 0, this switch connects the PN junction to ensure that it is always reversed. It is used to obtain the depletion capacitor model of the PN junction. The normal capacitor C is connected with the switch being closed when the voltage VDG is negative. Around a PN junction, we have the space charge represented here by the electric charges plus and minus Q. For simplicity, I assume that the P and N doping were equal, so the ρ charge density was also equal and the Q charges were distributed over the same distance W on either side of the junction. The electric field can be obtained from the equation divergence of the electric field equal rho over epsilon. By integrating the constant charge density ρ, the electric field increases linearly from 0 to Emax at x equal W, then returns linearly to 0 at x equal twice W. By integrating the electric field, we obtain the internal built-in voltage VBI generated by the PN junction. Delta V is equal to rho multiplied by W squared divided by epsilon. Note that delta V is the internal built-in voltage VBI plus the external voltage applied to the diode. The charge Q is equal to rho WA, where rho is the volume charge density, W times A is the volume, and A is the surface area of the capacitor. Replacing the term rho with the expression rho as a function of delta V, we can find the capacitor value by writing Q equals C multiplied by delta V. After simplification, we obtain C equal epsilon multiplied by A divided by W. Thus, the space charges plus Q and minus Q distributed over a distance of 2W are equivalent to a capacitor whose two plates are separated by a distance W, which is half the space charge distance. From the rho equation, we can obtain W as a function of delta V. Replacing W in the capacitor equation with the expression in red, we obtain a capacitor inversely proportional to the square root of delta V with a factor of K. To get an idea of the nonlinearity, we plotted the curve y equal 1 over the square root of delta V. I want to thank you for your attention. After looking at power switching, in my next seeker tutorial number 72, we will look at the ideal three-phase inverter. So, see you soon and stay tuned.